Thank you, Lynn and Dr. Raj. Thanks very much for the introduction. I'm Devan Iyer. I go by Devan, and I want to appreciate the organization IEEE NTC Miami chapter and IEEE EPS and EMBS student chapters for organizing this event and sponsoring this event by IEEE NTC. So what I would like to do this afternoon is to give you a quick snapshot on the technology application and trends, market trends, the broad spectrum of 5G, IoT, and I would also connect some of these applications to automotive, industrial automation 4.0, and medical and healthcare applications. So that's my objective, and in the next 45 minutes or so, I will do that. And I spend probably in the last 5 to 10 minutes covering some of the leadership qualities that are needed for aspiring students. Particularly there are student chapters who are co-hosting this event. So I want to spend some time on that as well. So as the outline says, I would go through the trends in technology and applications. What exactly is the system integration and the approaches that are being taken in the industry between system on chip and system in package. I would cite some examples on sensor integration, antenna integration for millimeter wave modules, particularly on the analog front-end modules, and the importance of chip package co-design as well. Okay, if I start with Internet of Things, this is a busy slide, but I just wanted to hit the important point that 5 billion IoT connections by 2025. So in the next 5 years, you are expecting to see greater than 5 billion IoT connections in the domains that are shown here: connected building, connected industrial applications, retail applications, asset tracking, environmental monitoring, smart utilities, mobile health, which is important from the healthcare point of view, that connects to the wearables, edge computing, gateways, smart cities. This connects to the vehicle-to-vehicle communication for automotives, smart parking, traffic sensors. So if I look at the top section of the slide, that are primarily connecting between automotive, health, and smart cities and smart industrial automation. And the bottom section is connecting primarily to factory automation. So creating a global ecosystem and connecting always on connectivity, machine-to-machine communication. So some of you would have heard about, those who are in the computing world of things would be working on cobots. They are actually between robots, how do you communicate? Or robots and human interface communication. So that's the bottom section that I'm trying to emphasize, where the industrial automation is moving in big swing there. Okay, this is, keep this in mind. I will come back to this during my course of the lecture, some of these application specifics. 5G trends and market penetration. Everyone knows about 5G. I don't have to explain what is 5G. But the good news is 5G is happening right now. If you look at last year and this year, 37 million units shipped with 5G, 37 million units of smartphones shipped in 2019. The projection was 238% increase with the real unit was, there was a growth of 238% expected, but the expectation got affected by purely because of COVID. And then we see only 125. As we are finishing the year, we will finish with 125 million units of 5G phones shipped. And that's going to go up to 250, 400, and 525 in the next 3 years. So what is projected is the next 5 years is 5G execution. Okay. If you were to really look at when did we start with 5G research, that was 2010. So it took about 10 years to get all the research into prototypes, into real products. So the expectation is by 2030, you will have 6G, and the research is just beginning to start. I will show you some of the examples of 6G while we are talking about 5G, what is expected in the 6G research. 5G execution cellular platforms, Intel, MediaTek, HiSilicon, Qualcomm, Samsung, they all have their own 5G execution cellular platforms. What are the key attributes and technology trends in 5G? Latency, peak data rates have gone up, frequency bands, the sub 6 gigahertz frequency bands and millimeter wave frequency bands. Both are being R&D in terms of research and development onto millimeter wave modules is happening. You have dual uplink waveforms, OFDMs. You have carrier aggregation. What we call as carrier aggregation is the multi-carrier links are happening today. In a way that your smartphones have got 4 or 5 types of antennas that are needed, from Bluetooth to Wi-Fi to cellular infrastructure, right? So these are multi-antenna where you have to have antenna plexers like duplexers. If you really look at the analog front-end modules, you have LNA, PA, switch, and duplexers and triplexers. Now we have antenna plexers, which means you have multi-antenna using MIMO technology. So these are all happening in the context of 5G. And these are implemented in the user equipment transmit and receive power. What enables this is multifunctional system integration. I will explain that in a minute, but keep this 5G demands for system integration. The next important thing is industrial automation. So when you talk about industrial automation, what we come across is Industry 4.0. So I have put some building blocks here: data analytics, wireless, and where do you store the data? In cloud computing, sensors and Internet of Things, industrial automation, AI, artificial intelligence, augmented virtual reality. And I brought in 3D printing purposefully because you will have to have manufacturing. At the end of the day, all these things need to be manufactured, right? You can have all these things in prototypes and PowerPoints and in the lab level research. But what industry would look for is, how am I going to do this in high volume, right? So 3D printing is an enabling manufacturing technology. Keep that in mind as well when we talk about Industry 4.0. So if I really look at it from computing, analytics computing, communication from the wireless, sensing and Internet of Things, what I showed in the earlier foil, factory automation, AI and virtual reality, enabling this machine learning and whatever we are talking in terms of the AI ML context, and last but not the least, the manufacturing. And that is what I schematically showed in the bottom side. How do you go in with wearable electronics, with sensors into it, blockchain for resource planning and supply chain management, computer vision, I talked about cobots, I talked about IoT sensors for supply chain, and last but not the least is predictive machine analytics from the data analytics and your augmented and virtual reality and AI combined. So we are at a place where we are trying to bring in multi-domain systems, right? The system engineering is getting complex because these are in multi-domain. I'm talking about computing, I'm talking about communication, I'm talking about sensing, I'm talking about AI, enabling the software for the hardware that needs to work on, and last but not the least, important aspects on manufacturing technologies. So that is the type of challenges for this decade, 2020 to 2030. You are talking about multi-system domain integration and how do you make this happen? So this cannot be done on a single chip. Definitely there needs to be module integration, and your modules can be system in package type of modules, which I will cover that in a little bit later. But I'm trying to set you the tone where the systems are coming from and what is the complexity as researchers or industrial engineers. When you join a company, they will be talking this every day in and out. Now, medical devices. Some of you have the background, some of you would be interested in knowing this. 3.7 million medical devices in use today. Okay, connecting to and monitoring various parts of the body. And these are in vivo devices or in vitro devices. Active implantable medical device control stimulation and or precision medicine therapy. So I put a closed loop here. And IoT is becoming Internet of Medical Technology or medical things, IOMT, system simulations. Collecting data from medical devices and medications and biometrics to modify therapeutic window towards best care option. Whether it is for the older community, old age population, or for those who are in demand, how do you get this transmitted, right? So you have devices, you have medicines, you have therapeutics, and on the right-hand side, what I'm showing here is that hospitals and home care is one application. You have prevention of disease, right? One is who are already having the disease. How do you protect them? How do you take care of them? How do you get them out of the hospital by providing them? How do you prevent the device? Then digitization. This is where the electronics comes in. From wireless point of view, IoT, 5G technologies, whatever I just talked about, a culmination of that is what we call as digital transformation, digitization, all the words that we hear. Then last but not the least, individual responsibility. It's my data, self-measurements, self-diagnosis, self-monitoring, and remote communication. If I have to be at home and I need to do this myself, I need to monitor this myself, whether it is my age that is preventing me not to go to hospital on a daily basis, or maybe I am not able to walk and go there. So there are different situations that prevent you from going to hospital. Even now, under the COVID-19 situation, many of these treatments are happening at home, right? So that is individual responsibility. So the bottom line I wanted to communicate here is, or come across to you guys, is that we are at a place where we want these devices to communicate, control, compute, and monitor, right? And the good thing is 97% of Wi-Fi adoption in hospitals today, which is the good news. 10% of medical devices enabled with Wi-Fi today. Medical devices are enabled with Wi-Fi. Still 90% is open. To make this digitization happen, we have to do a lot more work to do that. So I just wanted to connect what I just said so far, IoT and 5G, to the medical devices domain. Okay. I cannot leave this talk unless I talk about automotive electronics. So for this decade, 2020, 2030, I have tried to give 5 important aspects of automotive: safety, power electronics or powertrain, body comfort and lighting, advanced driver assist systems, and infotainment. Right? I tried to color them in different colors, and each color you will see multiple text messages here, and they are all connected to the sensors, communication, or power. It will have some sort of sensors when you talk about, anti-lock braking, lane departure warning. Lane departure warning is something to do with advanced driver assist systems, right? Blind spot detection is something to do with your body comfort lighting, or you may have to connect with that safety aspects, right? Electric power steering, it is connected to power electronics, right? So there's a lot happening on the power electronics side as we are moving from 12 volts battery to 48 volts battery in automotive electronics. There's lots of changes that are happening on the control system side, on the power system side. There's a huge intake of silicon carbide based devices, 3-5 compound based devices. Gallium nitride on silicon carbide is coming in full swing, capitalizing on the mobility of gallium nitride and the high thermal conductivity and the field strength of silicon carbide. GaN on silicon carbide is happening. Silicon technology itself is pushing towards the FET devices to higher voltages and power. So there's a lot happening supporting the automotive electronics. There's lots of opportunities to do research and development there as well. So coming to sensors, power, and communication on advanced driver assist systems, ADAS, infotainment and cluster, and the cluster system, and the body electronics and lighting, and last but not the least, the hybrid or electric vehicles and the power electronics associated with electrification of the vehicles. And I have listed some of these things that are pertinent to each one of those building blocks in automotive: advanced cruise control, entertainment systems and head-up display, security systems, and seat position control for body light electronics and lighting, and battery management, electric power steering. They are all applied to hybrid electric and powertrain systems. So why am I saying automotive in the context of IoT 5G? So IoT 5G and healthcare are connecting to the automotive. So today, you want your blood pressure to be monitored while you're driving. You need to have that monitoring system and communication system inside your car. And that is what is enabled through IoT and in future with 5G. Now look at just to give some examples of within power and communication electronics. So LiDAR, camera modules, radar systems, millimeter wave radar systems are happening now. Today, 77 gigahertz millimeter wave automotive radar have been released by companies like NXP, Texas Instruments. They all have that. They're all pushing the envelope to millimeter wave into higher frequencies. This is the cumulative average growth rate, what we call a CAGR. You see a tremendous growth in these areas. If you look at the power electronics side, battery management system, onboard charger, battery junction boxes, e-motor, inverters, converters, they're all seeing growth in the next 10 years. So again, the bottom line message is power electronics and communication electronics play a significant role in automotive in the next 10 years. Manufacturing, I cannot leave without talking about manufacturing. So there are a tremendous amount of manufacturing challenges. I talked about manufacturing challenges when I talked about industrial automation. Now again, I will give another example of a manufacturing challenge in the context of automotive. All automotive car makers, they need zero defects. They're really, really expecting zero defects to be there. And their slogan is not just a slogan for OEM, it is a must have. So industry, if you are going into industry, they will say, I want zero defects parts. I want zero defects components. That zero defect components is translated into systems, subsystems, modules, devices, processes, materials, right? The entire supply chain have to work in sync to get zero defects, right? It cannot be a zero defect in system unless you have zero defects in devices and modules, unless you have that in materials. So the entire culture is changing now. So zero DPPM is a common word, which means zero defects parts per million. But now the automotive industry is looking for zero parts per billion, right? Zero ZPPB. I don't want any defective parts in billions of units. The implication of that for companies is that if you are violating that zero ppm, DPPM or zero DPPB, your parts will not be accepted by the customer. So the implication is understanding the quality needs, understanding the reliability, and upfront understanding of the failure modes. So you need to understand why my device is failing, why my material is failing, why my process is failing. Understanding the failure upfront and design for reliability, we call DFR, and design for quality so that your manufacturing would be zero DPPM or zero DPPB. And that is clearly the manufacturing challenge that industry is facing today. To get to that levels of quality requirements with the complexity of multi-functions. If I have a bio device that needs to be integrated with a control device or a communication device or an IoT device, I need to understand that I'm going to bring in two systems and I'm trying to integrate. How do I get zero DPPM manufacturing for an automotive environment? That is what I'm trying to combine in this lecture as well. Okay, very important to talk about AI research needs. It's a pretty, too many words here. I apologize for that, but I would try to combine what is the salient aspect of what I try to cover here. The edge computing device on the top center portion. If I move to the top right section, somewhere in the middle of the, on the right hand side, I talked about medical devices, signal processing devices, biomedical applications, medical imaging. So if you were to really look at medical imaging and spectral imaging, hyperspectral imaging, there's always a trend towards miniaturizing this huge equipment. If I have a spectral imaging equipment that takes half of my office room, how do I make this into a sort of a desktop or even a sort of a laptop type of size? That will be a fantastic exercise. And that is where system miniaturization is helping in the spectral imaging these days. On the left-hand side, I've covered quite a bit on the energy aspects, computational intelligence, and multi-agent systems, ubiquitous computing. Where am I heading towards? The bottom line is we have a lot of AI-based research happening in the software side of the world. Now, if you look at the hardware aspect of it, Mukesh Kare from IBM, he talked about future of AI systems, and they have started an MIT MTL seminar. He talked about IBM AI Hardware Center. IBM has started artificial intelligence hardware. It's not just a software that we need to talk about. We need to make sure that the hardware also goes in sync with that. A combination of, they call it bits and neurons. Bits is nothing but mathematics and information, and neurons is nothing but biology and information and AI systems. So they're trying to combine what I just said in terms of how do I combine the mathematics and computing aspects? How do I bring in the information technology and AI systems combined with biology, right? Which is exactly what this IBM AI Hardware Center is doing. And it is in full swing. Lots of support from IBM microelectronic device to materials, implementation of nanomaterials, and taking it all the way into hardware, electronics, processors, computing applications, and communication. So it's a fantastic effort that is developed by IBM in the context of bringing AI hardware. All right, so what am I trying to summarize here from what you have heard for me in the past 20 minutes is IoT intelligent edge devices require technology integration. So this is the future as presented at the IEEE 6G Summit. At the bottom of this slide, I talked about enablers. What are the enablers? Your device materials, device electronics, electronic devices, packaging, systems, sensors, they are the basic elements supporting. You need the enablers like software security, software privacy, hardware security, interoperability. Then you have the system architecture. So those are the enablers. And why are we doing this? We want 5G transitioning into 6G in the next 10 years. When you guys, as students, you guys go into companies, and the companies who are really looking at roadmaps, moving from 5G to 6G, the same latency, dual uplink, your carrier aggregation, your antenna integration, your radio chips enhancements, connecting with IoT, where you want connected devices and objects, you want interoperability, sensing and sensing-based operations. We will have more challenges on multi-modal sensors, because then sensors are, it's a proliferation of sensors. It's not just one type of sensing. You have multiple types of sensors. That's what we want called, what we are calling as multi-modal sensors. Supporting on the software and hardware aspect I just presented, knowledge-driven, automated, unmanned, and analytics. So radio, systems, analytics. They differentiate the future systems, what we call as wireless intelligent edge. It's a fantastic way of looking at what is going to happen in the next 10 years. All right, so to summary, this is my way of looking at it. When I look at research needs driven by system integration advancement, what are the research needs for the next 10 years? From smart health point of view, sensing, terahertz radios, edge computing analytics leading to heterogeneous integration. Personal experiences, you want more and more in your wearables, wearable electronics, sensing systems, renewable energy. You don't have to have bulky batteries attached to your jacket while you are jogging. So you want some sort of renewable energy systems, which are happening. Machine vision and cybersecurity. You don't want to be hacked while you're on the road. So there needs to be some security systems attached to it. I talked about automotives. We are moving from level 3, 3.5, 4 semi-autonomous vehicles today to fully autonomous vehicles, which will take us into level 5. That would encompass multi-modal sensing, system integration, SWAM AI, and terahertz radio. Automated factories would need different types of sensors, design automation, AI hardware, and process automation. Computing systems, digital AI cores, analog AI cores with optimized materials, algorithms development, and hardware, all leading to heterogeneous integration. So heterogeneous integration is where you have multiple functions that needs to be integrated at the chip level or package level. Today, chip level is giving way to package level for heterogeneous integration. If you were to talk about 20 years ago, there was no RF CMOS technologies. So when we wanted to integrate CMOS and RF, we had to put them as two chips, gallium arsenide chips and CMOS chips, and make a module out of it. Today, some of those things, and to a greater extent, RF CMOS has brought in as an SoC, system on chip type of technology. So that leads me to system integration needs. I like this cartoon and the picture presented by Dr. Wally Rines, and who was a mentor CEO. Predicting Semiconductor Business Trends, he has come up with a fantastic book last year. And this recognizes the difference in the needs of different design disciplines. You have analog domain, digital domain, pure domain. You have mixed signal domain. You integrate a system. You have the software. You have to look at the mechanical aspects of system integration as well. Thermal aspects and thermomechanical aspects. You have to look at the manufacturing. And that is what is predominantly what we call as a system integration need. And believe it or not, system companies are now the fastest growing foundry customers. So if you go to foundries, TSMC or UMC, they have been approached directly by system companies, right? And there is a growth of 5-year CAGR growth. If you look at system companies grow by 70% directly working with foundries, right? And this is what has been in that book, nicely depicted by Dr. Wally Rines. So I would encourage you guys to read this book, which gives you an idea about where semiconductor business trends are happening and where we are heading towards. So given the background of where the technology is and the trends and what exactly the type of complexity that we are dealing with system integration needs, I would very briefly take you through the fundamental aspects of system integration in the form of system on chip and system in package. So systems and semiconductors are the center of a new era. I explained to you why we call it as a center of a new era from the aspects of the 5 different things that I talked about. System on chip and SIPs are complementary. They are not competing, they are complementary. But they are trending towards more and more multifunctional system integration and miniaturization needs. You have to have a good understanding of co-design, materials, multi-domain technologies. What do I mean by multi-domain technologies? You are trying to bring in gallium nitride on silicon. You're trying to bring gallium nitride on silicon carbide, right? For different applications, could be for power, could be for RF power, could be for pure high frequency applications. So depending on which domain you're talking about, you're trying to mix and match the 3.5 and silicon, just as an example, right? And the process integration is becoming more and more complex. And advanced packaging technologies are enabling us to get into heterogeneous integration in this mix of technologies that we are bringing in, right? In the context of what I just talked about, AI, bioelectronics, automotive electronics, industrial automation, we are moving into smart transportation with zero emissions, zero fatality, zero congestion, with enabling smart sensors into agriculture, infrastructure, healthcare. We are moving into a smart everything. We call it a smart everything. People, devices, homes, cities, industries, and on, right? So these multifunctional ICs or system on chips or devices where we have integration, or we can have a system integration coming from the context of digital and wireless. You have integration between high voltage and power. You have low voltage and power. You have sensors and biochips for various applications. So you are in the midst of bringing competing technologies. Once it was competing technologies, now we are trying to bring them as one system, right? In the domains of computing, communication, commercial, medical, automotive, industrial, and military and aerospace. So what it means, SoCs, classifications today, if you were to really look at, they have the building blocks of analog processors, RF, memories, and peripherals. You have all the control loop mechanisms and data paths and data processing all coming together, right? The 3 classifications of SoC as I see today, they are multi-technologies, what I just mentioned, power efficient technologies, low power, medium power, and then you have a classification of high performance SoCs. Now, are all the technical challenges being addressed? No, not yet, but there are, as we try to put in more and more functions on chip, your challenges are also increasing, which is what an engineers are supposed to do. I mean, no challenges, no engineering, right? So what are the technical challenges in SoC that we are trying to address today? Design for verification, test, and manufacturability. Reduce noise margin. You want the noise margin to be as low as possible in the midst of having more and more functional integration. Higher mask and tooling cost. As you are trying to bring in more and more functional integration, your mask cost goes up. You will also have to deal with IP and legal aspects of bringing functionalities from different experts or different companies. You will always be challenged with the yield at the wafer level and development time and cost. Increased crosstalk, coupling noise, reflection noise, switching noise will continue to increase as you go in for and more functional integration. Yield, I mentioned about it. Power management. How do you manage power, low power, medium power, high power in a single chip, right? How do you manage the low voltage and high voltage? What isolation needs are required at the chip level? If you were to bring in isolation at the chip level, you can have capacity-based isolation and so on and so forth. But there are challenges associated with 10 kV, 13 kV, 15 kV, 18 kV isolation needs. How do you manage that, right? You have to have a comprehensive system level simulation between digital analog, analog RF, analog millimeter wave interfaces. Okay, so there's a tons of research that are happening to compensate for the challenges that are happening in the system integration at the chip level. Now, if you transition into package level, so package trends are driven by product segments and system miniaturization. So package comes or sandwiched between chip and system, right? On the wafer, between wafer and system, you have package. So if I were to look at 30 years ago, where we were having, 20 years ago, not that old, video cameras and things like that, flip phones, and now we try to integrate multiple functions. And in the transition mode at the bottom of the slide, you are in the race of having more and more of integration that are happening. And we are at a place where we have intelligent cars, intelligent smartphones, mobile internet devices. On the bio world, we have lab on a chip, portable medical imaging devices, right? What next? What next is what I showed in the first 8 foils, right? Where we are heading towards from where we are today. And packaging technology would act as a key enabler, whether we are talking about computing communication infrastructure where performance, power, and cost. You look at my 1, 2, 3, 4, 5 here. I have given consumer, computers, automotive, spacecraft, and bio. And I try to highlight and make it bold. If I were to really look at biotechnology or bioelectronics, I will come in with reliability and size as my number 1 and 2 choices, right? If I were to go for consumer and portable application, what you and I go to a shop and buy things, cost comes in. Performance, you look at your performance of the device, or the laptop, or the iPad, or whatever or the smartphone that you are interested in, right? Computers, communication, internet, infrastructure, if you look at it, performance come in, performance and power, and then cost. So depending on the type of applications, your package technology also would differ. And that is what we show in this picture here. System in package integration technologies. You can have stacked dies, wire bonded interconnect, flip chip interconnect, device on device. Hynix has integrated, there are 8 to 20 wafers stacked together today to get their memory chips out, right? Along with that, there is a lots of wafer level packaging process, whether it is a fan in or fan out wafer level packaging processes. And I just use this foil to differentiate between a standard packaging solution like a chip on chip, wire bonded chip on chip package versus a wafer level packaging process, what I showed at the bottom of the foil. Okay, so why am I showing this? There are enabling system integration in package as well, which gives an industry, a company, a flexibility for faster turnaround time, lower cycle time in manufacturing. You have a better yield and testability because each individual die can be tested compared to your system on chip. Now, sensor system. So I've given you some introduction of where the market trends and where the technology trends are. Now I gave you some introduction on system on chip versus system in package. Now I will apply one of these into an application domain like sensor system integration. All sensors would need this. You have a receiving side and a transmitting side. Your real world is monitoring or a temperature sensor or a pressure sensor, position sensor, touch sensor, speed, flow, humidity, sound, light, identification. Whatever I have shown in the blue side of the world is all the sensors. Then you have the electronics for amplification, data conversion, A to D, D to A converters, interface electronics. Then you have the wireless connectivity, whether you want a Bluetooth connectivity or a Wi-Fi connectivity, or you want to connect millimeter wave antennas to your system, or you have a transmit receive. And then you have the entire analog front-end module in this wireless connectivity module where you have the LNA, PA, switch, and filters. People have started using BAW filters and SAW filters. So that's a lot happening on the wireless sensors and connectivity world of things. Then you have the processing side. You can have the digital signal processing, embedded processing. Then you have a power management, which optimizes your system performance from efficiency, responsiveness, and reliability. And this is the entire sensor system integration. If you were to really look at how does my sensor system look like, this is how it looks like. Okay, I just wanted to give you a feel of for the students who are interested in listening to this to understand that, right? I just took a biosensor-based electronic system as an example. Some of you have worked on it. Some of you are very familiar with this. So the type of biomolecules that you're going after, whether it is enzymes, antibodies, DNA, RNA, or tissue or cells, those are your biomolecules. So you have a mechanism to have a specific target molecule, which are highlighted in red, and the one in blue are the non-specific target molecules, which can be eliminated upon washing. And then the most important thing is the signal transduction or the signal conversion. You have different mechanisms today. You can have a conductimetric, impedance-based, resistance-based, weight-based, optical means, acoustics means, or thermal means. And then you have that mechanism to the electrodes that enable you to capture these molecules and amplify based on whether it is an electrical amplification or a thermal amplification or an optical amplification. You have different mechanisms of using that technologies like MEMS and photodiodes and so on and so forth will enable you to do that. And last but not the least, what I showed earlier in the sensor interface electronics, whether you want a data readout or a wireless connectivity, your electronic interface will take care of that. And depending on, oh, I'm sorry, I think I lost, let me get back to where I am. I pressed the wrong key. Almost there. Let me be careful. Okay, so again, a biosensor, depending on what type of biosensors you're going after, you can have that signal transduction or signal conversion unit and then go from there. And I just go through this quickly. I'm sure some of you in the university environment would have worked on it or would be working on it for capturing the metal nanoparticles, the interior of the DNA for thermostability. There are magnetic biosensors. There are quantum dots that can be used based on cadmium telluride or indium telluride or indium arsenide. The beauty here is the optical means of using quantum dots can be covalently linked with biomolecules such as DNA, RNA, antibodies, and so on and so forth. And you also have multi-wall carbon nanotubes, or carbon nanotubes can be used to capture this. So depending on the type of mechanisms that you use, and I'm going through it in a bit faster way because I'm sure some of you would be working on it or have worked on it to capture this and amplify it. But the bottom line I wanted to communicate here is how do you integrate them in a system integration? Once you have the signal amplified, you have to have a sort of an ASIC or an application specific IC that needs to be a part and parcel of a mixed signal design system, right? That has to have an ultra low power consumption, 60 microwatts, because you don't want your biosensor system to be super heat dissipating, then you have to figure out how to take the heat out of it. So the beauty there is to design some of these ultra low power sensor electronic chips, right? Suitability for a large spectrum of biopotential signals, whether you are going after EEG and ECG or ECG and EMG or EOG, depending on one or two of these mechanisms. How do you have the right electronics going with that? Low noise, high common mode rejection ratio, capable of filtering these devices. At the end of the day, you want the body monitoring wireless system in package that enable you to get to what you want. You want a wireless sensor, you want a readout, you want a radio link, and an antenna, a suitable antenna that goes along with the system, and low power consumption. So those are some of the challenges I want to highlight here from a biosystem integration point of view. We talked about front-end modules, analog front-end modules, where you have all the systems. What I wanted to show you is antenna integration. How do you integrate the antenna? And I want to show you 3 examples which have been realized on a front-end module, analog front-end module, along with the LNA-PA switch and the diplexers and all those front-end module components. Along with that, you have integrated a 300 gigahertz horn antenna. Horn antenna has got the best advantages of bandwidth. It covers the high frequency range, gives a fantastic efficiency. Here is what NTT has done and is published, where they have an LTCC horn antenna on a low temperature co-fired ceramic substrate. Another example, 2 examples here, one from Infineon on their embedded wafer level BGA package, where they have a broadband bow tie antenna in the 120 gigahertz and 240 gigahertz. 2 broadband bow tie antennas working in the 110, 170 and 220 to 325 gigahertz frequency range. At the bottom, what I'm showing is a TSMC. As I said, foundries are also working on system integration today. They're integrated fan out, where they have integrated 60 gigahertz and 120 gigahertz on a wafer level fan out WCSP configuration. Fantastic work by both these companies. And here is an example of what TI, Texas Instrument, has done a couple of years ago. They found out as a product where a 4-layer package, a BGA package, is used with all the other electronics, the millimeter wave IC designs. ICs have been integrated along with a circular patch antenna integrated with their power amplifier. And they also have created a high impedance surface. It's constructed with the 3 top levels of the package to suppress any substrate modes and prevent unwanted radiation. So it's a more of an EMI suppression as well is incorporated into this module. So again, I just wanted to show you some examples of how system in package or system integration technologies are enabling the integration of millimeter wave and terahertz antennas. What enables all these things is chip package co-design, which is a critical factor in multifunctional system integration. If I were to really look at the signal integrity, power integrity, EMI management in a multifunctional chips, there could be sensor chip, there could be RF millimeter wave chip along with the low power chips. How do you isolate them? How do you integrate them? How do you characterize them? Keeping the signal and power integrity aspects. 3D antenna, I talked about antenna integration, matching networks, transitions, modeling the microwave and millimeter wave transition is a challenge. interconnections to passives, high-Q inductors, integration, and three-dimensional wiring, low parasitics connections. All these are part and parcel of your electrical design. And I also brought in high voltage, low voltage isolation. In the same module, you have low voltage and high voltage. How do you bring in the isolation at the package level, right? So that's the electrical challenge. Along with that, you have thermal management. If you are bringing in high power electronics along with low power electronics, you need to provide some active methods of cooling, liquid cooling, spray cooling, thermoelectric coolers, and so on and so forth. Or you can use the standard heat spreaders, thermal vias, manage the passive methods. And there is an intermittent method of having active heat sinks by having micro fans attached to it. Or you have the opportunity to manage with thermal interface materials like thermal gels, phase change materials. There's a lot happening on phase change materials research for thermal interfaces. So along with the electrical side that I talked about and thermal management, you also have to look at thermomechanical challenges, right? That brings in different material sets. You always bring in polymer metal interfaces, ceramic metal interface, or metal interfaces in packages that are very common in ICs and system packaging. So interface characterization is important from their thermoelastic behavior, plastic behavior, creep, viscoelastic, fracture, fatigue, failure modes, understanding the failure modes. So as I said at the beginning of this seminar, I talked about design for reliability, understanding the failure modes from electrical failures, mechanical failures, thermal failures, understand them, and then co-design. So I would always emphasize that, and companies have started co-design teams. Most of the semiconductor and system companies have got co-design teams where they bring in electrical engineers and mechanical engineers and material scientists together in a team to understand this and have the design modeling capability from different aspects to have the co-design, which will make your package, which will make your device, package, systems robust in manufacturing. So with that, I would switch over very quickly and give the students some advice on technology and management as you are looking for jobs, as you step into the companies. With my experience, I can give you a quick snapshot on that as well. So when I look at key leadership qualities, you have to be a good guide, right? You need to be in the forefront, mentoring your juniors. You have to inspire, motivate, right? As leaders, some of you are listening to this talk would be already managers and leaders. You would motivate your aspiring engineers who have just joined your team. And last but not the least, influence. So this goes as you gain more and more experience. You will be looking for a guide in the beginning, right? And then when you are experienced, like 5 to 10 years, you will start motivating your juniors. And then once you are matured, like you get into like 15, 20 years, you will start influencing your decisions, influencing your recommendations into the company, inside the company. That is the 3 leadership qualities at the different levels of your career. And I always believe that a leader is one who knows the way and who goes the way and who shows the way. You have to know where you are leading your team to. You have to stick to that way, the path that you are setting. You have to have the good vision to set the vision, guide your team, you mentor them, coach them, and lead them. And then you have to show the way and stick to that, right? All leaders generally keep mentors. And when leaders lead the army, mentors lead leaders' thoughts. It's very important for you to have a mentor with you when you are trying to lead the team. The soldiers follow the leaders and leaders follow the mentors, right? That's the way corporate works. That's the way the companies work. And I'm sure that is where the organization works, whether it is an academic organization or an industry organization. Leaders and their mentors reboot each other by asking right questions at the right time. Questions are triggers. For me, in my career, I would always like to ask questions to myself, and I always trigger questions in meetings so that, the questions would generate ideas and they convert the implicit assumptions. Questions would have some implicit assumptions. Say, why is this person asking questions, right? Okay, that may have some implicit assumption. Challenge the assumption. And that with explicit reasons while tapping energy of a mentor. So the mentor is asking the leader a question, the leader is turning to his team and asking the question, and it generates some discussions around there, right? And that is where the ideas generate. Innovations generate out of questions and in the discussions. So mentors make the leader think harder. Always you make your team to think more and more hard. And that generates more and more ideas, generate concepts, new concepts. Whether it is an academic setting or an industry setting or a corporate setting, it doesn't matter. Unless you ask questions, the people will be waiting for, hey, what am I going to do next? What am I going to do next, right? And that is where exactly comes from mentors. They make the leader think harder, show him or her the total picture, the big picture, and then highlight the flip side and install the confidence in his or her decisions or inside building confidence for him or herself. Students aspiring to join companies, skill set and qualities, always connect your skill set. Whether you are a designer or a material expert, process expert, assembly, reliability expert, it doesn't matter. Understand why you're doing what you're doing. Very important. You have to ask, why am I doing this? What is the application that I can foresee in that, right? If you do not know, ask questions to your mentor. Be a good team player and a good listener. You may be a member of a small team, 5 people, 8 people, 10 people, 100 people, big and complex team, it doesn't matter. Understand your role, understand your deliverables, what is expected out of me, and commit to the schedules. That is the first and foremost thing that would be expected. Whether you are inside a project, a research project, there are certain deliverables, there are certain committed schedules. Understand your role, work on that role, be a good team player and a good listener. Knowledge on subject matter is important because you do masters, you do PhD, you come in as a fresh engineer to a company. Your knowledge on subject matter is important. You have to be thorough. You have to be humble. Your humility matters. Accountability. You are accountable for certain things and you will be counted on that. And you have to have the integrity while you're delivering your committed things. And they are all critical factors for success. You know, I mean, for you to be successful, you have to keep these things in your mind. You don't have to wait for any seminar to happen. You look for it, attend internal, external seminars and be in the forefront to learn. You are on a continuous learning process. Even if you're joining a company, hey, I got a job, I'm going to do this. But open your mindset, be broad, listen to whatever seminar opportunities, internal, external seminars, attend team building events and contribute. You have to be a good team player, contribute service to the community, not necessarily always to the company, but you can be community support on weekends, right? So that makes you a better leader again. Now, technology and management ladders to climb in your career, right? Build career in technology ladders, build career in management ladders. If your passion is technology, you don't have to forcefully say that I want to become a project manager. There are opportunities in companies for you to develop a technology ladder path. You can become a fellow of a company, technical fellow of a company. There are people who have made significant contributions by having innovations, patents, and publications from companies being on the technology ladder. There are people who after 5 to 7 years, they switch into a management ladder by doing project management, section management, director, vice president, and so on and so forth. I kept to my heart technology always. I continue to publish papers. I continue to innovate. I have patents to my credit, but I also contributed to the management ladder and grew in the technology ladder and management ladder. You can become, you can be in the management ladder by managing technologies for the company, right? So leadership always exists in technology and management, right? I will pause here and take any questions. I'll be more than happy to answer any questions on the technical side or on the leadership side. Thank you for listening.
Thank you so much for Dr. Iyer's presentation. So if you have any questions, please unmute yourself to ask, or you can type in the chat.
Hello.
Yeah, go ahead.
Hello, Dr. Iyer. Good evening. Can you hear me?
Yes.
Yeah, hi, I'm Kefayat. I'm working as a graduate student at FIU. So I have 1 or 2 questions for you, if you don't mind to answer them.
Sure.
Yeah, so I'm working, basically, I've joined last year, so I'm working as a PhD student. So I'm working basically building systems, or let's say, for example, some of the 5G things that you told about, like the carrier aggregations and all these noise figures and margins. So I build systems, and we are trying to build like code division multiplexing or CDM technologies for wireless communications and to utilize the huge spectrum at 5G and millimeter wave, right?
Yes.
So I have this question, like, what do you think? Like, I started like building with millimeter wave antennas till the RF front ends, and we are testing our products and design the PCBs and all the chips. And like, we are not chip designers. We simulate in AWR or Cadence, and then design the PCB board and then fabricate and test our system. So
Yes.
what do you think? This kind of expertise are these industry level, and are they going to help us as graduate students during our internships, or what are the opportunities that we will be able to land up with these expertise? Do you think so?
Yeah, absolutely. You're right on a target. I mean, when you explained your project description, you know, for analog front-end module, antenna integration is a part and parcel. I briefly mentioned about the antenna plexers. So we need multi-antenna. It's not one antenna now anymore. I think your smartphones have got 4 antennas. You know, moving forward, it's going to be even more complex. So you are right on dot in terms of your studies. I would suggest you should look for internship. You said your first year, second year? I missed that part.
Yeah, second year.
Yeah, even you're in your 3rd year, definitely you should look for internship opportunities. And you should, as I showed some examples, it's not just the system companies who are doing this today. Even foundries Like I showed an example of TSMC integrating millimeter wave antenna as a part of their wafer scale process, right? So I think there is an on-chip antenna integration for millimeter wave and terahertz. There is off-chip antenna integration. There are pluses and minuses. You know, I mean, just to give you some example, on-chip antenna is great. You know, you can have miniaturized, micro-miniaturized antennas. As you go higher up in frequencies, your antenna dimensions are going to be even smaller and smaller. So on-chip antenna gives that advantage. But on-chip antenna has got some limitations in terms of positioning the ground plane, where you want to position the ground plane when you have a silicon back end of line. Structures are all fixed. You don't have much room to play around with your inter-level dielectrics and separations. But on package, you have that flexibility to place your ground plane and reflector for antenna. I think that's an advantage for off-chip antenna. And you know, so and in off-chip antenna, you have different types of package solutions. You can do wafer level packaging. You can have it on laminates, and you can have 2 transmit, 2 receive, 1 transmit, 3 receive. So you can have different combinations of that. On-chip antenna, for example, you have limitations on the isolation from the active circuitry, MMIC circuitry to antenna radiated emissions and coupling. How far you can go on an on-chip, that is limited, whereas on a package you have more flexibility. So the companies are weighing a lot now as you speak. You know, what are the right ways of integrating this for 5G? So, I mean, the answer is straightforward. You have opportunities knocking at your door. You have to look for different types of companies, system companies. You can go for semiconductor companies. You can go for even foundries. I hope I answered your question.
Correct. Thank you. One more question, Dr. Iyer. I was thinking and reading papers last few days about CMOS integration of antenna, just antenna on CMOS. But don't you think that there is a huge chance of silicon, high dielectric losses, silicon losses of building antennas on CMOS? Do you think that's going to help? Should I go for it or not?
Yeah, I mean, I would suggest you to discuss with your supervisor because I don't want to deviate your
I was just having a general idea, like how the CMOS losses is going to contribute to the antenna and its performance.
Yeah, I think the antenna feed is you need to really look at how are you planning to feed your antenna on a dielectric loss if your substrate is lossy. I think that could be a challenge. And yeah, I mean, I would stop there because I would like you to do some research in that direction. But there are, you know, if you are going outside silicon, there are some opportunities to look at for low dielectric loss materials as your substrate.
Okay, I would just bother you with one more question. It's more a bit of general. So do you think there are chances for guys like us who does the system simulations and the system hardware design, like FPGAs? I mean, I integrate FPGAs and ADCs, DACs, and antennas with my system. Do you think this kind of people have opportunities at Texas Instruments, like companies like Texas Instruments?
Yeah, I mean, not just limited to TI. I mean, you have TI and then NXP, Analog Devices, Qualcomm, Broadcom. They are all in the domain of system integration, like what exactly you defined, right?
Okay,
The standard, the typical communication companies and the semiconductor companies, they all have needs for your background. Yes.
Thank you very much, Doctor. It was nice talking to you. Thank you.
No worries. Thanks.
Yeah, I have a question.
Yeah, go ahead, Alex.
So yeah, what are some habits you cultivated in order to identify these opportunities and to recognize, for example, where the future is or where the direction of this technology could be?
Your question is more towards where the future is heading towards from system integration point of view?
Yeah, what are some habits you cultivated in order to identify these opportunities?
What qualities? I missed that question.
Yeah, what type of habits?
What type of habits?
Yes.
Okay. From a student perspective, I would always say that you need to develop, as I said, you know, keep your opportunities open in terms of try to learn. This is your learning phase. You are still in the learning phase of your career. You know, be broad, not to get too much narrowed down into one area. And one thing I can tell you, the future is going to be interdisciplinary. So people are really looking for the backgrounds of design and process, or process and materials and reliability, right? So I think it's extremely important for you guys to have the broader spectrum of things rather than 30 years ago when I was in the school, or 40 years ago. You guess my age now. So I think, you know, if you were to really look at what we were taught is more deeper knowledge in the one area, now things are changing. Things are becoming more diverse, and you need to have a broader mindset. And when you are in school, try to learn interdisciplinary courses, right? You have to focus on your area of research. That's important, but try to take 1 or 2 courses outside your sweet spot, you know, even if it is something to do with understanding a little bit on the outside the domain. That would help you when you get into companies.
Thank you. I have one more question.
Sure.
What are some of your favorite books you like to read?
Yeah, one thing I would say is on the leadership side, I would say the ex-GE CEO, Walsh, right? Jack Welch has written a fantastic book on leadership. I would suggest that. And I recommended on the semiconductor business trends, I would say Dr. Wally Rines has written a book and released last year on semiconductor business trends. It's not just the business trends. Dr. Wally Rines, knowing him very well, he has worked for Texas Instruments. He has worked for, he was the CEO of Mentor Graphics. You know, he has the depth and breadth of knowledge base on semiconductors. I would recommend that, or if you want to really understand where this is going. And to answer your earlier question, you know, what are the important things on the trends that are happening? That book is good. I have given the reference in the note as well, lecture notes.
Thank you very much.
I think due to the time limitation, we may have the last questions.
Can I go with a question?
Sure, go ahead.
Sure.
Hi, Dr. Iyer. First of all, thank you so much for the wonderful, inspiring, and very informative talk.
Thank you.
So actually, I said I'm working on analog computing. So actually, now we are exploring how these analog accelerators are used in machine learning as machine learning accelerators. So you talked about automotives. So in automotives, and especially with self-driving cars, what do you think? What are the opportunities for analog AI? AI hardware, AI accelerators.
Yeah, great question. I think I gave you that purposefully. I put that on the lecture notes on AI hardware and IBM AI Hardware Center, which they launched, I think, a year or two ago. Can't exactly remember, but it's pretty new, with the intention of making these type of AI-based hardware not just limited to computing application, but open up into other applications like automotive. So AI hardware is going to play an extremely important role in autonomous driving. I think where you are coming from, analog computing world, and get into the mixed signal domain, that would also help you. When I say mixed signal, you know, analog front end is one area where you have an interface from RF and analog. That's what I call by mixed signal. That would help you to position much better off in the next 5 to 10 years, right? So the mixed signal design focus would enable you to understand the different applications, not just limited to computing, but into industrial automation. I gave you some examples on how analog computing and cobots are going to work together, right? And that machine-to-machine communication in a factory environment is extremely important. When you have 20 machines doing the same operations, you have tons of data created today. Managing the data, analyzing the data, and distributing the data, and then filtering what is needed for today's manufacturing. At the end of the day, if an operator comes and looks at it at the 9 o'clock in the morning or 8 o'clock in the morning, and when he leaves the floor at 6 p.m., he will have tons of data. But what is needed for tomorrow when the machines have to work in the way that they expect the machines to work? And that is exactly what is needed for this decade. They are struggling today for machine-to-machine communication, and each machine has got tons of data. And if I have 500 machines running in a factory floor, how do I get all this data and analyze them and get ready for tomorrow? That management of the data is all nothing but computing. And then that selective computing needs what you just said. And that is where the AI-based applications and AI-based hardware will enable you to do that. In an example I just gave it, right? You gave me the autonomous driving. I gave you another example of industrial automation. Both would need the same.
Yes. Yeah. It's really, yeah. There are a lot of opportunities, I guess.
Absolutely.
And, yeah.
This next 10 years is going to be highly interesting to see how things are happening.
Yeah. From your talk also, like, I got a lot of information. It's really helpful. Thank you.
Okay, good to hear that. Thank you.
Thank you. And if we have time, okay, are we out of time? If not, I just have a simple question.
Please go ahead.
Okay, so it's about management and technology. So how did you actually balance both while going up in the technology ladder and at the same time the management ladder?
Yeah, my mentor helped me to really, at some point, they noticed the quality of management in me, not just the technology aspect. I have the passion for technology, but that is how I became a technology management leader. In a company, you need manufacturing managers, you need sales managers, you need different types of applications, right? So they found the person with PhD in my field of expertise and management capability. And that is where the synergy came in. And as I said, the mentors are important. You know, you have to have good mentors saying that, hey, Devan, you have this capability, you understand technology, but you also have an opportunity to lead in people. and lead projects. And that is how I grew in that ladder. But I continued with my passion. I attended conferences. I continued to publish. Later on, as I grew up in my ladder, I became more of an invited speaker and keynote speaker in conferences, which is a good thing to happen, because once you learn how the conference runs and how you get benefit out of this, right? So I think that helped me a lot. Yeah.
Thank you, Doctor. It's really inspiring. Thank you.
Yeah,
all right, nice talking to all of you. Thank you.
Yeah, thank you, Dr. Iyer, for your valuable presentation. And I think that's the end of the web seminars.
Thank you, Linton. Thank you for hosting.
Thank you again for everyone's attendance.
On the class, which is starting in a couple of minutes, the BME 5803 class. So again, thank you very much. Very inspiring, and I think many people could connect with what you said. It was really very important for students to see the breadth and the visionary skills and the hard work it takes to succeed. Thank you.
Thank you, Dr. Raj. Thanks for hosting. Thank you. Thanks for having me.
Bye, everyone.
Take care.